that we'll explain as we go through this whole Cambium College process is to get that application that's far away from you geographically to you and your local device so that you can use it and enjoy it. Next one, please, Ray. So this is just to kind of drive this point home, because sometimes when you look at more of the detail of how computer networks work, and it's very easy to get lost in the detail, and sometimes it can seem that you're doing things just to do them, or because you have the technology to do so. But it's always worth remembering that these three blocks are really the only point of the network. The whole point of the network is to connect these two on the left and right to each other. So I just wanted to emphasize that here so everyone's on the same page with that. Next one, please, Ray. So, we talk about computer networks, and I'm sure, again, this won't be news to many of you, but, a various wide range of technologies can be used to construct computer networks as we know them today. It's very easy to break these two into two distinct camps for our purposes, which would be wired and wireless technologies. I'm sure that basically everyone here is familiar with Wi-Fi on some level, probably LTE and Bluetooth as well, and some of you probably also familiar with Ethernet if you've plugged in like a desktop PC or a smart TV or an internet router or anything like that lately. But just to break those two into two separate camps. So these, even though they're wired and wireless, depending on whether you need to have your phone be moving around, obviously that's not going to work very well if you have to have a wired connection to it. But fundamentally, whether it's wired or wireless, a computer networking technology is still just trying to achieve that same basic aim. It's still just trying to get an application to the user, essentially, regardless of how it does it. That's its goal.
Alex, we did have one question come in, and could you just define what Wi-Fi and LTE are?
Sure. So Wi-Fi stands for wireless fidelity. It's essentially a short-range wireless communications technology. I'm sure all of you have a Wi-Fi router in your home. This is how you're probably listening to me tell you about it at the moment. It would be typically how people inside a home would access the internet. LTE stands for long-term evolution, and it's essentially the most recent cellular technology. If you think about more outdoor focused and much longer range wireless connections, so those would be from the likes of AT&T and Verizon, for example. So whilst Wi-Fi would typically be inside your home, and you would use your, perhaps for instance, your Comcast cable connection and have a Wi-Fi router on that, which lets you access the internet. LTE would be, what you would subscribe to on on your mobile phone, to the likes of AT&T or Sprint or Verizon for kind of outdoor use and use when you're going around. Does that make sense?
Yes, thank you very much.
Oh, sorry, this is the next one, isn't it? Yeah, so I wanted to bring up the topic of network topologies here. So really a topology in computer networking defines how a network is logically and then also sometimes physically structured. And I've got some examples of this in a moment, but basically some very popular network topologies that you will run into throughout learning about networks, and if you ever install a network yourself or just trying to decide which is the right way to go with a network design. These are some of the ones that you'll run into. For instance, a bus topology, hub and spoke topology, also known as a star, and it will become clear why it's a star when you see the picture. Excuse me, a line topology, a mesh. You can get full and partial mesh. Again, I'll show that in a moment, but that will become clear when you see the picture. And tree topology. So network topology is very important because it really defines, I suppose, how the network really passes data between its constituent parts, if you see what I mean. This will become more obvious if you can go to the next slide, please, Ray. So in all of these diagrams, basically the green lines are, if you will, the network infrastructure, if you will, and then the green circles with the black outlines are end devices. So think of, say, the top circles as, for instance, desktop computers, and maybe the bottom ones are smartphones, and then they're all connected together by this green network topology, essentially. So bus topologies, they're not seen as frequently today as they once were, but they're a pretty core fundamental part of just general network topologies. Basically, you can see that the network really runs kind of in sequence and connects to all of the nodes, as I call them. So the nodes would be the end devices connected to the network, whether that's a PC or a excuse me, you know, a smartphone, anything like that. So for the purpose of this, think of those as network nodes, and then think of the parts of the network that connect those nodes to each other as the network infrastructure. So you can see the infrastructure here basically runs left to right, and it has a bunch of branches and offshoots, one to each node, and you could see that to get to, say, the node furthest on the right, if you think of data coming in on the left, it basically has to go past all of those other nodes, but just stays on that main horizontal network path until it gets to its intended node. Yeah, so if you want to go to the next one, Ray, these make more sense when you, sorry. What?
Yeah, we do have one question that came in, Alex,
Sure.
and the question is this bus topology that you're showing here, is it wired or is it wireless? And I think what the question is about is that the green line that connects each of the nodes. Is that wired or wireless?
So that's a very good point. So really, these could be either wired or wireless. I would say for the bus topology in particular, it's much more likely to be a wired connection, because where the bus topology typically comes in is for some older networking technologies where this horizontal green line would be a single strand of copper cable, essentially, and then to connect each you know, PC or printer or whatever the node is to that, you would physically connect a kind of smaller branch-off cable into that main cable, and then, you know, they start to split off into the different you know, into the different vertical lines that you see here. So this one is more specific to wired, but there are many examples in the following topologies where they could be either wired or wireless, and I'll explain those as we go through. Does that answer the question?
Yeah, there is one follow-up question to that. One person is asking, can you give one example of where you would commonly find a bus topology today?
So I must admit, bus topologies are not typically used today very much, but it's still important to conceptually understand them, to understand network topologies. Where they were originally seen is in some of the original Ethernet networks, what was called thinnet or thicknet, where you had this horizontal line here would be a single basically piece of copper cable that ran through the office or through the home, wherever the network is installed. And then to install each one of these nodes, the network engineer would go out and physically tap the cable, as in physically connect a spike through to the copper conductor, and then he would have one of those little vertical offshoots to his PC. I hope that answered the question.
Yes, it does. And we've got some more questions, but I think as you move through, you'll find that we've got the answers coming up.
Okay. If I get to when we get to the end of just these topologies, because I see one of the questions here, we'll wrap up those ones if that's okay, and just so we get them all covered.
Great.
So the hub and spoke here. So there's what I should have here, to be honest with you, is another node probably in the center of this to provide the hub, if you will. But essentially, what this network topology does is basically say that, okay, you have a central point in the network which is responsible for basically sending out and receiving data from all the other network nodes. So those nodes aren't connected to each other, but they're all connected back to one central point, and that central point handles the connectivity between all the other nodes kind of as a proxy. So I must admit, apologize for the mistake here on my part. I should have a circle in the middle of this, so my apologies there. But hopefully you can see the intention of the diagram here in that, you know, let's say the node at the top and the node at the bottom, if they want to contact each other, they would contact this node in the middle of all of them, who would then pass the messages on. So a good example of this one is very commonly seen in wireless technologies, for example, and Wi-Fi is a very good example of this. So your home Wi-Fi router is basically doing a hub and spoke topology very much like this, where the individual nodes are the kind of the spokes of the wheel, and then your Wi-Fi router is that middle hub piece that passes the information between the devices. So line topology, kind of similar to a bus and kind of similar to a hub and spoke in many ways. If you think of it as kind of a hybrid between those two. So an example of this would be kind of a relay network. So let's say you have a wireless network that's operating over a very long distance, and you need to have multiple radios across the length of that connection that you're trying to make to, you know, cross that distance essentially. So let's say maybe you want to cross, you know, let's say 50 meters, let's say, just for the sake of argument, and each one of your radio links here can do, you know, 10 meters. So you've got, you know, the one on the left connecting to the one next to him, then he relays it to the one next to him, who relays it on, until it reaches its destination, essentially. So each of these nodes does have connectivity to each other, but it's not, apart from the one directly adjacent to it, it doesn't have a direct connection to it, essentially. So you can imagine if the middle node here fails, and the same as if the middle node in the hub and spoke fails, then the network essentially will not be able to provide you that end-to-end connectivity. You might be able to connect from, say, the one on the far left to the one on the kind of the middle left, but then they won't be able to connect to the two nodes on the right. So yeah, mesh topologies are interesting. So what I've tried to illustrate here is both a full mesh on the right, where each node is connected to every other node, and a partial mesh on the left, where, so if you look at on the diagram on the left, the node on the right-hand side of that left diagram, he can connect to all the other nodes in the network, but only by using the bottom node there as a proxy to get to the other two. Whereas on the right, he has 3 connections, 1 to each node. So essentially, he can, at will, connect to any of those as he wants to. And you can imagine that in the one on the left, if his single link to the bottom node goes down, then he's essentially cut off from the network, and none of the other guys can contact him, and he can't contact them. However, the one on the right, he'd have to lose, you know, basically all of his 3 connections to, you know, become completely cut off from the network. So there is, you know, redundancy advantages with a full mesh. There's some, you know, overhead of additional connections, and a lot of the time some of the redundant connections won't be used and things like that. But you know, just to compare the two, I think that's a useful comparison. So just, I think this is the last one I have here. So this is just a tree topology, essentially. You can see at the bottom, the node at the bottom is basically the root of the tree, if you will, and then it branches off into, you know, many more, basically almost mini networks when it gets big enough, in the sense that, you know, you can see how if you built this up a few more levels, it would start to look like a tree branching out in various different directions. And then that's, it's an interesting topology, because you know, the number of branches in a given section may not be completely the same between left and right. For example, on this part, we've got one more connection on the left-hand side of the tree than we do on the right, and you could have vastly different networks all connecting back to a central point. So the tree topology is kind of interesting. I would say of all of these topologies, probably the one, particularly in wireless networks, that you're going to run into most often is probably the hub and spoke topology that we talked about, simply because that is more commonly used for some of the most popular wireless technologies. So I just wanted to cover the question here about the ring topology. Ray, did you want to read that one out, or do you
Yes.
want me to do it?
No, I'll get it, Alex. The question is there also a ring topology, or is the token ring setup considered a different networking system?
So I like this question. So a ring topology is definitely a network topology. Bear in mind, I by no means covered all the network topologies in this. And if you start to get into very specific, different types of individual network topologies, like there's multitude of different flavors of the tree topology alone, for example. Token ring itself is a set of networking technologies that basically fulfill the role of Ethernet in that they are a wired networking technology. It's basically an alternative to the Ethernet protocol set that we find very commonly in things like desktop PCs, PlayStation 4s, things like that. It uses a ring topology basically in its design, but you can have networks, whether wired or wireless, that aren't using token ring as a technology, but that are still using a ring logical network topology. So I think it's helpful to separate those two a little bit. So token ring always uses a ring topology, but you can get ring topologies that are made up with technologies that aren't token ring. Does that make sense?
Great. We do have one question, one clarification question about the mesh network. And the question is, I'll bring up the mesh network images again. Can you please quickly restate which mesh was full and which mesh was partial?
Sure. So the one on the left is a partial mesh because not all the nodes have connections to all the other nodes. You can see the on the left diagram that rightmost network node kind of out on his own there only has a connection to the bottom node. You can see on the one on the right that he has a connection to all three nodes, and all three nodes have a connection to all the other nodes essentially. So hopefully that clears that one up.
Great, thank you very much, Alex, and thank you everybody for asking the questions. It really just makes the presentation much more relevant when we can be sure that we're getting to what you want to know. Alex, I think that's all the questions we have about the topologies. How about if we move on?
Okay, sure. So I wanted to talk a little bit about network protocols. So, protocol is a word that you will probably be hearing very frequently, whenever you look at particularly networking. You might hear it quite often in technology, but in networking it's very important because if you think about what a network is, it's essentially two distinct separate devices trying to communicate with each other. So, a protocol is basically an agreed upon language used between devices. So if you think of it kind of similar to English, for example, I'm able to communicate with, someone on the street because I can say the same words, that I know that they mean the same thing, I can create sentences using the language, and we have a shared understanding of what those mean. It's essentially the same thing with network protocols, although being computers, they're a little bit more picky than us. So essentially, without a very clearly defined and consistent protocol, network communication is basically impossible. I mean, you can imagine trying to have a conversation with someone who thinks up means down, right means left, and it's very difficult to really get anywhere with that, and especially if you're a computer who doesn't have that ability to kind of infer, meaning from tone and hand gestures and things like that. So it's an important point to mention, I think. Also, it brings up the importance of what are known as industry standards. So there's some network protocols and kind of standards that are agreed upon basically by everyone who makes or operates or sells computer networks. Things like the Internet Protocol, Ethernet, Wi-Fi, for example, are all very, very standardized and agreed upon technologies and protocols essentially. And then there's a whole bunch that are what we would call proprietary, where they may be a standard or a protocol, but only within a certain company's products, for example. So Apple had a protocol called Apple Talk, which was to communicate between Apple devices. Then if you had a Microsoft PC, that couldn't speak Apple Talk. So just wanted to mention that that importance of protocols, and then also of standard protocols as well. So you all know you're speaking the same language and that you can talk to each other, which is how the network is going to work. So on the network protocols, so there's a very commonly used model that's very helpful to understand how basically network devices and networks in general are structured, and then how they work. Throughout any study or work on computer networks or computer network devices, you'll see this model a lot. It was one of the things that I spent a lot of time making sure that I could basically memorize and jump to at any point that I needed to, because it really helps you understand things very easily when it comes to network technology. I should point out that as well as Ray's mention of me as the product manager, I also have a master's in network engineering, and this does still come up even at the master's level. And when implementing things in real life, you'll always be referring back to this OSI model, Open Systems Interconnect model, very frequently. So it's worth just making sure that you get a good understanding of it. So basically what this model is it breaks down a network device or a network, any kind of computer networking functionality, down into 7 logical layers. So the purpose of doing that is that by separating functionality into these layers, one layer can change. For instance, I'll get to an example of this in a moment, but it's very useful to be able to change different layers in this OSI model kind of stack of 7 layers without having to change any of the others. And I'll show the actually I'll show it now. Actually, could you skip to the next one, please, Ray? Got ahead of myself for a second there. So this is the OSI model. Don't worry too much at the moment about memorizing all these words, but if you think about the example of why this is an important capability to have, that separation of functionality into 7 different layers. So if you think about, for instance, the physical layer. So an example of something at the physical layer would be, is it a wireless network or is it a wired network, right? So it might be surprising to find out that because it's organized in this way, what the model lets you do is basically switch out your wired network that maybe you were using as your primary network connection on your desktop PC 10 years ago to Wi-Fi on your smartphone today. So you've gone from wired to wireless, and you don't need to change any of these other layers at all. So you don't need to change the network protocols at the higher levels. You don't need to change the software application. Netflix, for example, doesn't know or care whether you're connecting to it with a wired connection or a wireless connection, for example, and that allows them to focus on, developing the application, and they don't have to worry about every other part of this this model, essentially. So kind of going at it from the bottom up, so layer 1 is the physical layer. So this is the actual physical data transmission medium, as we would call it. So whether that's a piece of copper wire, whether that's radio waves, infrared, whatever, fiber optic cable, that is the part of the network that is physically moving some kind of electrical charge or some kind of indication of data between 2 physical points. So if, for instance, take a wired network, this would take the shape of a copper cable connecting, say, 2 PCs together, and then representing data being sent between those 2 PCs by using a series of electrical impulses on that cable. Excuse me, just give me 2 seconds. So that's layer one. Layer two, I'll kind of skip to these a little bit because it's a little bit too much detail, I think, to go in at the moment, and this will make a bit more sense when we go into some of the later sessions. But layers 2, 3, and 4 are basically concerned with making sure that you're talking to the right end device. You're talking to the right, basically make sure you're talking to the person who you think you're talking to. Making sure that the data you're trying to send is delivered to the right person, and then also making sure that it's delivered reliably. So that's really 2, 3, and 4. And then 5, 6, and 7, you'll notice that they're slightly different colors. Layers 4, 3, 2, and 1 are typically called the network layers. The ones above that would be typically referred to as the application layers. So a lot of the time as a network engineer or someone building networks, often your ability to interact with things is often limited to 4, 3, 2, and 1. And then the people creating applications such as streaming video services and things like that would typically be interacting with 7, 6, and 5. Hopefully that made some kind of sense.
Well, let me just try and clarify. So right now, we are all on a network listening to this webinar that you're delivering. And if I understand correctly, what you're saying is that layers 5, 6, and 7, that's the application, the presentation, and the session, would be the actual software that we're seeing on the screen.
Mm-hmm.
And then the transport, network, data link, and the physical are all exactly how we are getting to that connection. Whether I'm sure there's some people that are over a wired connection right now.
Mm-hmm.
I personally am wireless, but because the transport, network, and the data link are all very common, the physical can be very different for each one of us. Is that a good way to look at it?
That is a very good summary. That is basically entirely correct, and I really like the example of using the the webinar that we're doing right now as the example. So you're entirely right. This GoToWebinar software setup would be 7, 6, and 5, and then the rest of the layers 4, 3, 2, and 1 are really how we're able to access the webinar.
Good. Well, then let's try for the next slide.
Sure. So I wanted to talk a little bit about just the internet in general. So this may seem obvious once you see them broken apart, but the internet stands for internetwork. So it's really a network of networks. It's a large system of a large number of interconnected networks. So I bring this up because often people think that the internet is this one big network, or it's this one kind of amorphous thing that just lets you connect across the world, and it's really not. It's kind of an interesting beast in that it is formed really by the sum of all the networks that are trying to connect to each other. So for instance, your home network may not be part of the internet, but if you connect to the internet through, say, Comcast, for example, Comcast's network is a part of the internet, and then they connect to other networks to allow you to basically access anything in the world online. This will make more sense if you go to the next one, please, Ray.
Sure.
Probably should have put these on the same one, but so really to make that internet work, if you think of that network, internet rather as basically let's say 10 big networks that all need to connect to each other to make the internet actually exist. Basically how that works is, so let's say AT&T has a network and Verizon has a network. So what happens is they come together and they agree to peer with each other, as it's called. So basically this means that AT&T and Verizon agree to connect their networks to each other because they see it as being mutually beneficial. AT&T's customers can access stuff that services and applications that Verizon's network has, and vice versa. So it's mutually beneficial, and this is really how the internet is created, basically. These peering relationships exist basically across continents and basically across the whole world, which is what allows you to take something, say, on AT&T's network in Chicago, and be able to access a website that may be in Britain on British Telecom's network, because those two network operators have this peering relationship between them. So there's interesting pictures actually online of internet peering maps. If you look those up sometime, those are very interesting because it kind of gives you an idea of the scale of individual networks that are connected to each other to form the internet. I think it's pretty interesting to see.
Alex, would there ever be a case where somebody would have their own network that's not connected to the internet? Why would they want something like that? What would they do with it?
Yeah, so I think I had something like this on the next slide. If you could just click to that one, please.
There you go.
Oh, I was getting ahead of myself there. So I suppose just to answer your question, yes, so it's interesting to think about networks in that way as both either public or private, or even sometimes a hybrid of the two. So if you think of a public network, let's say, would be something like Comcast's, cable ISP network. So you pay them a fee, and you're able to basically use the network more or less as you wish within the terms and conditions, obviously. So that's what we would call probably a public network, although admittedly one with a fee. A private network would be a network, for instance, if you drive around or you go around, for instance, any major city, you'll typically see a lot of security cameras around, right? Things on street corners and things like that. So, that's a video surveillance system, and those are all connected by a computer network. But obviously for that use case, video surveillance data is very sensitive. You don't really want people being able to access it as they wish. So you would want that to be a private network where you restrict access to only yourself or only a very small number of people who you want to have access to it. So there's a few reasons why you would have either a public or private network. A lot of it's due to the level of privacy that you want. Maybe you're handling very sensitive data. If you think of maybe a military network, that's a very good example of one that you don't want to be publicly available. So that's kind of the breakdown between those two. It really often comes down to privacy, the types of applications that are being delivered over the network, and really just the intent of the owner of that network. Does that answer your question, Ray?
Yes, thank you very much.
So on this slide, really just examples of networks. So we kind of talk about networks, and I wanted to start with the kind of somewhat abstract kind of conceptual background to them. We look at the topologies and kind of what the purpose of a network is and all that kind of thing. But I mean, networks are very, very common. I mean, don't look at any of those topologies and think, I don't see something that looks exactly like that. I don't have any networks near me. I mean, like we talked about, a network is how, we're having this conversation now. It's how you can call, your grandmother, tomorrow afternoon. It's how you can do your, submit your homework online, stuff like that. Your typical smartphone can typically connect to 5 different networks at the same time across both short and long range options. Television and radio or other types of network. They might not be computer networks, but they're certainly networks which fulfill a very similar purpose, which is to basically provide access to things, whether that is digital computer data and streaming video and things like that, or whether it's a radio station. It's conceptually very similar. So something kind of amusing to do might be to sit there and say, how many networks can I think of that I've interacted with today, or can I just think of that I'm using at any one point in time? And it's really quite a high number today, to be honest. I mean, for instance, if you have your desktop PC connected to a wired connection, you've got 1. You might have your smartphone next to you that has Wi-Fi and LTE turned on, so that's 3. You might be wearing some Bluetooth headphones, that's 4. That's really quite a lot of different networks and different network technologies that you may not even notice day to day that you use all the time, and really make quite a positive impact on pretty much everything that you do. So, yeah.
Okay, well, I think that's, thank you very much, Alex. What I'd like to do now is just open it up to any of the people in the audience. If you have any questions about networking, or any questions about Alex and his background, now is the time that you can just type in your question into the dialog box, and we will go ahead and address each one of those. In the meantime, while we're standing by for a few questions to come in, I'd just like to remind everybody that if you join the Cambium Networks community, you can post any questions that you have at any time, and you'll find that your question may be answered by either Alex or myself, or even some network operator. The community is actually a very good way where you can start to meet network operators from around the world, ask technical questions, and watch any of the webinars that are there. And I'd encourage each of you to take a few minutes and go ahead and get to know a little bit about the technology, more by asking questions and interacting rather than having a large textbook in front of you all the time. Okay, we do have one question in the queue here, Alex, and I hope you're ready. I knew this would be about the OSI model. The question is, will we go into more depth with the OSI model, for example, layer 2 switches or layer 3 routers?
Yes, definitely. Please, if you're a bit more familiar with network technology, and you probably are based on the fact that you can say layer 2 switches and layer 3 routers, don't be put off at all by the fact that this one is perhaps a bit more introductory than you may have been expecting. It's kind of difficult at the start of one of these long courses to really gauge the level at which everyone's at. So hopefully this catches more people up to a common baseline, and then absolutely we go into more detail as we go through. So don't worry about that at all.
Oh, and absolutely, as we start to get into the applications discussions, there's going to be an awful lot there where you'll be able to really visualize it. One question also just came in: where can I get the recording of this webinar? We are recording the webinar right now, and tomorrow morning it will be on the Cambium community under the Cambium College and Foundation 01. We'll actually post the recording right there, and that's also an opportunity where you can post any questions that you have. Okay, let's see. Alex, we do have one question here, and they are starting to come in fast and furious. I'm just trying to hold on to one here. This question is, could you briefly describe your personal path from which college you went to how you got to be a product manager?
Well, my path is somewhat strange in that I started at Motorola, as it was, in 2008. I had not been to college or university, as it would be, as I'm from England, and basically managed to get in at a entry-level position based on self-study that I had done. And basically during my time there, I learned more and progressed through to more of a higher role in engineering, whilst working on my MSc in network engineering kind of in the background. I had a remote learning degree, basically, with the Open University, which is actually very good. So from that, I then went from kind of test engineering through to system architecture and design, which is also a very interesting topic. I then did some marketing activities as well, more on the technical marketing side, and then basically moved into product management. Hopefully that answers the question.
Great, thanks. And one of our member of our audience asked for the URL for the community, and that is community.cambiumnetwork.com. And I think there is a banner ad right there that says you can go straight to the community for the area for Cambium College, and you'll be able to find all the different sessions there. We did have one other clarification question, Alex, and that is, how does a star network differ from a mesh network? And let me just go back to those slides. So here's
Okay,
a
yeah.
map.
Yeah, the mesh one should do. So if you think about a star or a hub and spoke topology, those two are the same thing. So if you think about what that fundamentally was doing was it had one single central point, which all of the other nodes were connected to, and for each one of those nodes to contact another node, they had to go through that central node. So that central guy acts basically as a relay between each of the other network nodes. So as you can see in the mesh topology here, that's not the case. So as opposed to the hub and spoke where you would have just that central point is the only one connected to every one of the other nodes, in the mesh, you can see there, for instance, especially on the full mesh on the right here, each one of the nodes is connected to every one of the other nodes in the network. So they don't need to, have that central node as a proxy at all to contact each other. Hopefully that answered the question.
Great. One other question came in, and will we get a PDF of this webinar? I've got the slides. What I will do is actually post them to the Cambium Networks community under the Foundation 01 thread, so you should be able to find those. Let's see, this audience member, Omar, says, great presentation, important concepts, and it's easy for beginners to understand. So thank you very much.
Well, thank you, sir.
We do have this question that just came in from Laura. It says, can you give an example of an OSI model layer changing?
Yeah, so I was just about to say if you could go to the OSI layer one here. So the easiest example here is if you think of layer one, that physical layer. So that's really the layer that determines the actual physical medium, if you will, that we're using to transmit data. So if you think about wired networks and wireless networks, in a wired network, that layer one is a piece of copper cable, typically, whereas in a wireless network, it's a radio transceiver that it's sending and receiving data wirelessly over the air. So that's probably the easiest example of imagining an OSI model layer changing is just switching out a wired network for a wireless one. You're switching that layer one component, essentially. Does that make sense?
We will see. Another question came up from Dwight about the OSI model. It got my attention. Will there be more detail on the OSI model in future sessions?
I think that would be pretty useful. I think probably the most useful time to do that is maybe in a couple of sessions' time when we've gone through, maybe a little bit more detail about what each part of the model is. I didn't go into a lot of detail on it here because I was concerned that it would kind of it would kind of be overload at this point. But yeah, we can certainly go back to it and give you a lot more detail on that because, as I say, it is something you will come back to all the time. And the reason why this model is so useful and why it's persisted for decades at this point is because when a new technology or a new application or whatever it is comes along, all you have to do to understand it really in terms of its fit in terms of a computer network or a computer device is to look at this model and go, okay, it's in let's say layers 3 and 2, so I know exactly what parts it affects and what parts it doesn't affect, and that really does help you understand its impact. So yeah, we can definitely go back to the OSI model.
Okay, great, thank you. And one question we had is, will the recording include the slides as well? And yes, the recording is just like a streaming video, and that will be posted to the community tomorrow. Here's an interesting question for you. How did you start your career in wireless technology? Is that what you always wanted to do?
So I wanted to be involved in network technology, wired or wireless, really. So really, when the opportunity came up to apply at a company that was kind of at the forefront of developing wireless computer networking technology, I jumped on it pretty much. I was always pretty interested in network design, network theory, network architecture, topics like that. So really, yeah. I mean, I was looking around for things like network engineering. Whether that's kind of a network support or network design, just basically anything around networking at the time. And the opportunity came up to be basically a test engineer for wireless networking equipment that we make here at Cambium, and so I applied and went from there.
Great. And another follow-on question, Alex, is how much has networking theory changed over the last 20 years?
So it's interesting because theory, I would say, has not really changed to a fundamental degree at all in the past 20 years. If you look at particularly network theory, and then branching out into some of the much more in-depth mathematical arms of that, a lot of that was done kind of earlier in the 20th century by some of the kind of foundational computer scientists and some of the guys who worked on network information theory, Elgamal, stuff like that. The actual underlying theory, I would say, has not really substantially changed in quite a while because they did a lot of very solid foundational work. Information theory is also worth looking into if you're interested in that level of the theoretical underpinnings. Which covers things like what is the actual, Claude Shannon, for example, is a very noteworthy scientist and mathematician in information theory, and defined basically the limit of useful information that you can carry in a given amount of space or time, for example. So that was really all done earlier in the 20th century, and in terms of fundamental changes to the theory or the mathematics, not a great deal, to be honest with you. There's additional technologies and things that have been built on top of that theory that definitely show a lot of evolution over recent years, particularly in wireless communications. But those fundamental parts of for instance, network topologies or network information theory or graph theory, those haven't really seen a dramatic shake-up for a number of years.
Thank you. And I think we have one other question here that may be more relevant in one of our future sessions. And that is, what is the difference between full duplex and half duplex?
Okay. So in a full duplex, sorry, let me start with half duplex. That's probably easiest. So in a half duplex system, you cannot send data at the same time as you're receiving data. A good example of this is Wi-Fi, for example, where you cannot send and receive data at the same time. It may seem like you're doing so because it switches very quickly between sending and receiving data, but actually it's sending and then it's waiting, receiving, then it's sending, then it's waiting. Full duplex, on the other hand, allows you to do exactly what you'd expect, transmit and receive data at the same amount of time concurrently.
So probably, and that's for maybe folks where that's a completely new idea. Right now, as we're talking with each other, this is ideally a half duplex system where I'm talking and you're listening, then you talk and then I listen.
Yeah. Unless you're having a conversation with me and I start talking over you, then it's becoming full duplex at that point.
Exactly. We were just about to run into that as I talked over you a little bit. Here's a question about the mechanics of Cambium College. When and where will we take the test for this? Always good to look ahead. We will have a 50-question multiple choice test, and that'll be available starting in early November through the end of December. So you'll have probably 6 weeks to take it. And it certainly won't take that long to go through the test. It'll just be 50 multiple choice questions. And the idea here is just to check for understanding. We're not trying to catch anybody on anything. For those students or for those people who take the exam and pass with 80% or higher, It is Cambium's recognition to you that we will actually give you a high-capacity Wi-Fi access point that hopefully after the entire sessions you'll know a lot more about what it is than if you got it today. So there will be more details coming up about the test. There's no charge for the test at all, and there's certainly no charge if you win the if you earn the Wi-Fi access.
Mm-hmm.
We do have one last question that because I know time is running short, and this is one really about operating systems. And the question comes from Joshua. So Apple devices use their own language, and Windows Linux use their own language. Can you touch upon how these devices with different systems are able to communicate across networks or the world to each other, and maybe some of the devices and switches involved in making this work successful?
So I'm really glad you brought this up, because I think I may have introduced a little bit of confusion when I mentioned the AppleTalk protocol as an example of a proprietary protocol. So that's just used for some Apple-specific, just local device file discovery type communication. For your computer to say, access this webinar, for example, whether that's PC, Mac, Linux, whatever, the one that's very crucial for that are, if you look at this OSI model in particular, the ones that need to be consistent for that to happen are layers 3 and 4. You'll notice 3 is known as the network layer. So the intent of layer 3 and the most popular layer 3 protocol, and we'll get to more detail on this one in a future session, is IP, or the Internet Protocol. If you ever typed in an IP address for setting up a phone or accessing a game server or whatever, that's what this is. It's an Internet Protocol address. So unlike the 2 layers below it, at the network layer, the intention is that every device on the Internet essentially has a unique layer 3 address, if you will. And to connect to each other, they all use that same layer 3 protocol, IP, and they use that unique address. So I know I'm only going to talk to, Joshua in, Chicago, let's say, and I know it's him because he's got that unique layer 3 address. So this is what I was trying to get at with, standard protocols, in that AppleTalk is a proprietary protocol, so you can only use it just kind of locally. Let's say you connect your iPhone to your Mac over your local network. That would be an example of AppleTalk or another proprietary protocol. But to connect, say, across the Internet, you really need to be using an industry standard protocol, such as IP, to do that. And then once you're doing that, it doesn't matter whether it's Apple, Windows, Linux, Android, whatever. As long as they're all using that same protocol, they don't need to, translate between different languages or any of that. So hopefully that answers your question.
Great. We do have a number of questions coming up about applications. We're already at the hour, so let me just have, we'll just queue up one more question, and then I'll stay online and we can answer the rest of them that are in the queue. The question comes from John. What might be the link connection or noticeable transition from the bottom layers of the transport into those top layers where you go into the session layer?
I see. So you're asking about basically the interconnections between the layers, right?
Yes, sir.
So there's, and it gets into an incredibly long, detailed specification that I won't overwhelm you with at this point, but basically there are defined interfaces, if you will, between each one of these layers. So particularly for your question about, say, let's say you receive data. So when you receive data, let's say you're receiving a video file, right? So you kind of go up the model if you're receiving data, and you go down the model if you're sending data. So let's say we're receiving some data. So first we receive those electrical impulses on the copper cable. That's layer 1, right? We've got the physical indication of the data signal. Layer 2, we'll go into a bit more detail about what specifically Layer 2 is, but basically from layers 2 and 3, we figure out if it's addressed to us, and, if we're the intended recipient. If we are, we pass it up to Layer 4. Layer 4 basically intends to make sure that it is reliably delivered, so Layer 4 says yes, this was delivered without any errors or missed data. And then at that point, the network kind of shell, if you will, of that application data is essentially stripped away, and then the data it was holding, which then goes into the session, presentation, and application layers, is passed up to that software application at the session layer, which passes it up to Layer 6 to Layer 7. Hopefully that answers your question.
Great. Thank you very much, Alex. Thank you, everybody, for joining us. We will be back in 2 weeks where we'll talk about more of the foundations. If you do have additional questions that come up or other comments or feedback, please go visit the community at community.cambiumnetworks.com and go to Cambium College, and there you will find tomorrow morning we will have the video recording up of this session. We will also have the PDF slides available for you to download. And Alex and I will be there to answer any of your questions. I'd like to thank everybody for joining us, and special thank you to you, Alex, for kicking this off, and we look forward to seeing everybody in a future session. Thank you.
Thank you to everyone for listening to me.